Have you ever wondered, if air is all around us, why does it feel invisible? Welcome to Foe's Curiosity, where today we're diving into a question that has puzzled thinkers for centuries. Is air really nothing, or is it a tangible, measurable substance? Let's start with the basics. Air isn't just air, it's a mixture. A homogeneous gaseous substance composed of multiple elements and compounds. Unlike a pure substance or a chemical compound, air doesn't chemically bind its components into a single entity. Its main ingredients, nitrogen and oxygen, exist side by side, physically mixed, while other players, like argon, carbon dioxide, and water vapor, join in, each retaining their own properties. In fact, you could separate these gases using physical processes, like fractional distillation, a feat impossible if they were chemically bonded. For many practical purposes, like calculating airflow over an airplane wing or predicting weather patterns, we treat air as a uniform gas. But this simplicity hides an underlying complexity. Humidity, temperature, and trace gases all subtly shift its density, proving that air is dynamic, not static. Now let's talk numbers. Dry air is roughly 78% nitrogen, 21% oxygen, and just under 1% argon. Water vapor can range from almost zero in cold polar regions to up to 4% in humid tropics. Trace gases like carbon dioxide, methane, and neon, though minuscule, play outsized roles in climate, atmospheric chemistry, and even how we measure air's density for precise engineering. Imagine that, a substance you can't see, yet it shapes the weather, flight, and our very ability to breathe. But despite all this, humans didn't always recognize air as real. Ancient philosophers were baffled by the void. Aristotle famously said, "Nature abhors a vacuum," arguing against the very existence of empty space. Air, invisible and tangible, seemed to fit this idea of nothingness. Some called it pneuma, a vital spirit, hinting that people sensed its importance, even if they couldn't see it. Others, like the atomists, imagined atoms moving through empty voids. The debate raged for centuries, until empirical science stepped in. Empirical confirmation came when scientists began measuring forces exerted by air. Take the Magdeburg Hemispheres experiment, for example. Two metal hemispheres were fitted together, air evacuated from the interior, and, despite being separated only by a thin seam, they couldn't be pulled apart. Horses had to pull to break them free. Why? The external atmospheric pressure was so strong, unopposed from the inside, that it literally held the hemispheres together. Invisible, yes, but overwhelmingly powerful. Even simpler demonstrations reveal air's presence. Place a card over a glass of water, invert it, and watch the water defy gravity, held in place by atmospheric pressure. Light a candle under a cup in water. The contracting air inside creates a suction that pulls the liquid upward. These experiments show that air isn't absent, it's constantly applying force, even when we don't notice. So what makes air matter? First, it occupies space. Push a glass into water. The air inside prevents the water from filling the glass. Try inflating a balloon inside a sealed bottle. It resists because air already fills the volume. Next, air has mass. At standard conditions, it's roughly 1.2 kilograms per cubic meter. Measuring this is tricky because of buoyancy. The surrounding air pushes up, masking its weight. Clever experiments, like cooling a balloon with liquid nitrogen to shrink the air inside, reveal the true gravitational mass, proving once again that air is tangible. And of course, air exerts pressure. The collisions of billions of nitrogen and oxygen molecules against a surface create forces of about 1 kilogram per square centimeter, pervasive, constant, and measurable. Without these molecular impacts, airplanes wouldn't generate lift, balloons wouldn't rise, and even sound wouldn't travel. Speaking of which, sound is another way we experience air as a material medium. Vibrations from a tuning fork push air molecules which transfer energy to their neighbors in a chain reaction. This is why a vacuum is silent. Sound cannot propagate without a medium. Air is not just resisting motion through drag, it's transmitting energy, carrying sound, supporting flight, and enabling life itself. And finally, our bodies constantly sense air. We feel wind, detect drafts, notice pressure changes, and breathe in oxygen, all confirming that air is a physically real substance, even if invisible. Hot air balloons rise because they displace air. Airplanes soar by creating pressure differentials. Wind moves leaves and bends trees. These everyday phenomena are proof that air is alive with motion, mass, and force. In summary, air is no void. It's a multi-component, dynamic, measurable physical substance with mass, volume, and pressure. The ancients' inability to see it didn't negate its reality. Modern experiments, from simple water glass tricks to the Magdeburg Hemispheres, demonstrate beyond doubt that air is a tangible, energetic, and essential medium. Its invisible nature may fool the eye, but science leaves no room for doubt. Air surrounds us, pushes us, supports us, and powers our very world. And speaking of the world around us, why doesn't Mars have the same air pressure as Earth? What makes Venus so inhospitable? And why doesn't the Moon have an atmosphere at all? Why can't a parachute even work there? Let's start at home. Earth's atmosphere, that invisible ocean of gases, isn't just air. It's a living, evolving system shaped by 4 billion years of chemistry and biology. About 78% nitrogen, 21% oxygen, and a trace of other gases, including a mere 0.04% carbon dioxide. Yet that fraction controls our planet's climate, keeps oceans liquid, and makes life possible. The oxygen is the real clue that Earth is alive. It's made by photosynthesis, plants and microbes splitting water, exhaling oxygen into the sky. Without them, our air would look like that of Mars or Venus, silent and lifeless. Now imagine climbing through Earth's atmospheric layers. In the troposphere, where clouds form and weather stirs, temperature drops with altitude. 75% of the atmosphere's mass lies here. Then comes the stratosphere, where the ozone layer absorbs ultraviolet light and warms the air, a calm region where jetliners cruise. Above it, the mesosphere grows cold again. Meteors blaze there. In the thermosphere, solar radiation heats molecules to thousands of degrees, yet you'd still freeze because the air is too thin to transfer heat. Beyond lies the exosphere, where the atmosphere dissolves into space, a whisper of atoms drifting away. From here, Earth's air looks impossibly thin, yet it defines everything about our world. Now let's visit our neighbors. Venus, Earth's twin in size, took a darker path. Its atmosphere is 96% carbon dioxide, with surface pressure 90 times greater than ours. The temperature? 464 degrees Celsius, hot enough to melt lead. Venus's thick CO2 blanket created a runaway greenhouse effect. Its clouds are droplets of sulfuric acid, and its surface lies under a dim orange haze. With no oceans or tectonic plates to store carbon, the planet trapped its own heat and never recovered. Next stop, Mars. Here, the air is almost gone, less than 1% of Earth's pressure, still mostly CO2, but too thin to trap heat. Even the fiercest dust storm would feel like a gentle puff on your hand. The average temperature is about minus 60 degrees Celsius. Once, Mars had rivers and maybe seas, but when its magnetic field faded, the solar wind stripped its atmosphere away. What's left is a ghost, a whisper of air clinging to a frozen desert. It's striking. Venus and Mars share similar chemistry but opposite fates. One burns, the other freezes. The difference is density. The thicker the atmosphere, the more heat it traps. And then we reach the Moon, our silent neighbor. Here, our opening question returns. Why doesn't the Moon have air? The answer is gravity. The moon's mass is too small to hold gas molecules. Its escape velocity, just 2.4 kilometers per second, is so low that even gentle molecular motion can fling atoms into space. Over time, any trace of atmosphere vanished. What remains is an exosphere, a veil of isolated atoms like helium, argon, and neon. A cubic centimeter of lunar air contains about 10 quadrillion times fewer molecules than the same volume on Earth. That's not an atmosphere. That's emptiness. And in such emptiness, aerodynamics dies. A parachute, for instance, works because of drag, the resistance created when air molecules hit a surface. The physics is simple. Drag equals 1/2 times air density times velocity squared times a drag coefficient times area. On Earth, it works beautifully. On Mars, where air is 100 times thinner, parachutes must be huge, like the 21-meter canopy that slowed NASA's Perseverance rover. Even then, rockets took over for the final landing. But on the Moon, air density is effectively zero. Multiply anything by zero and you get nothing. No drag, no slowdown. A parachute there is as useless as a sail in a vacuum. That's why every lunar lander, from Apollo's descent module to modern probes, uses rockets for controlled descent. There's simply no air to work with. When we line up these worlds, a pattern emerges. Atmospheres are sculpted by gravity, magnetism, chemistry, and sunlight. Earth found a fragile equilibrium between them. Venus trapped too much heat and boiled. Mars lost its shield and froze. The Moon never had enough pull to hold air at all. Each world is a natural experiment, a test case of what happens when one physical variable changes. And this leads to the next question. If the atmosphere is the stage, what is the performance? Wind. How does air set itself into motion? Why does it race from high pressure to low, swirl over mountains, and roar across coastlines? And how do engineers learn to use or fight this invisible force in flight and design? Let's start with the simplest definition. Wind is air in motion relative to the Earth's surface. But that's a bit like saying the ocean is water in motion. True, yes, but the beauty lies in the why. At its heart, wind begins with sunlight. The sun warms the Earth unevenly. Some places get more, others less. This imbalance sets off a chain reaction. Warmer air expands, becomes lighter, and rises. Cooler, heavier air rushes in to replace it. That rising and sinking motion, called convection, is the engine behind the entire atmospheric system. But there's another subtle trick of nature at play. Moist air, which contains water vapor, is actually lighter than dry air at the same temperature. That means humid regions tend to have lower pressure, while dry, cool regions tend to have higher pressure. And it's from those differences between heavy and light, hot and cold, dry and moist that the invisible gears of the atmosphere start to turn. Air always wants balance. It flows from high pressure to low, pulled by what scientists call the pressure gradient force. That's the first great sculptor of wind. On a weather map, you see it as tightly packed isobars, lines of equal pressure. The closer they are, the stronger the force, and the faster the wind must blow to even things out. But as soon as the air starts to move, Earth itself interferes. Because our planet spins, every moving parcel of air gets deflected, a phenomenon known as the Coriolis effect. In the northern hemisphere, winds bend to the right, in the southern to the left. The faster the wind and the farther you are from the equator, the stronger this deflection becomes. Mathematically, the Coriolis force depends on the Earth's rotation rate and the sign of your latitude. That's why it's zero at the equator and strongest at the poles. When the Coriolis force perfectly balances the pressure gradient, we get a geostrophic wind, a steady, graceful flow moving parallel to the isobars, not across them. It's this balance that keeps jet streams snaking across the sky at hundreds of kilometers per hour rather than rushing straight from pole to equator. But closer to Earth's surface, things get messy. Here, the wind battles trees, buildings, hills, and that battle has a name: friction. This layer where friction dominates is called the planetary boundary layer, or PBL. It's the turbulent lower kilometer or two of the atmosphere where wind becomes unpredictable, gusty, and alive. During the day, when the ground heats up, rising warm air thickens this layer, mixing the air and creating gusts. At night, when the ground cools, the layer shrinks and the air settles into a calmer flow. Because friction slows the wind, the Coriolis effect weakens too, allowing the air to turn slightly inward toward low-pressure areas. Instead of gliding neatly parallel to the isobars, it spirals, creating the graceful dance we see in cyclones and anticyclones. And if you move upward through this layer, you can actually see the wind rotate with height, a clockwise twist in the northern hemisphere, counterclockwise in the southern. Beyond a couple of kilometers, the friction fades and the air joins the smooth, balanced flow of the free atmosphere once more. Here's something counterintuitive. Sometimes the wind gets faster at night. After sunset, the ground cools quickly and the air near the surface slows down. But the air just above it, now free from friction, can accelerate like a car suddenly freed from drag. This creates what meteorologists call the low-level jet. By midnight, this layer can produce winds 40 miles per hour strong, even when the surface feels still. These supergeostrophic flows, winds faster than the theoretical balance, are born from the night's decoupling between the cool, sluggish surface and the freer, faster upper air. It's a quiet, invisible race above our sleeping cities. To truly understand the wind, we need to see it, and that's where technology steps in. One of the most advanced tools today is the Doppler wind LiDAR. It fires a laser, usually around a wavelength of 1.5 micrometers, into the air. Tiny dust particles and aerosols reflect that light back, but because they're moving, the reflected light shifts in frequency. That shift reveals the wind's velocity, sometimes with precision better than 4 centimeters per second. By scanning in all directions, scientists can reconstruct a full 3D picture of the wind structure. And when multiple LiDARs work together using systems like Wisdom, they generate virtual towers of data showing exactly how wind vectors twist and stretch through the atmosphere. This technology is reshaping how we predict weather, design aircraft, and plan the next generation of urban air mobility. Wind doesn't move in a vacuum. It's sculpted by the land itself. Along coastlines, warm land and cool sea surfaces create the daily rhythm of sea and land breezes. But head toward mountains and the story turns dramatic. When stable air slams into a mountain range, it's forced upward, then down again, creating standing mountain waves that ripple through the sky. These waves can produce violent downdrafts, up to 5,000 feet per minute, strong enough to pull aircraft toward the ground. Beneath their crests form turbulent rotors, massive rolling eddies that make flight nearly impossible. It's here, above jagged terrain, that the atmosphere reveals its true power. Winds that combine speed, turbulence, and vertical motion in ways no flatland breeze can match. For engineers, wind is both enemy and ally. Its force can topple buildings, sway bridges, and test the limits of design. Yet, by studying it, we transform chaos into knowledge. Wind load analysis, the prediction of how structures respond to these invisible forces, is essential not just for safety, but for sustainability. With the planet's climate growing more extreme, engineers are learning to build smarter. optimizing shapes, choosing lighter materials, and using airflow to their advantage. In this way, wind becomes not just a test to endure, but a teacher. It pushes us toward elegance, toward designs that are stronger, greener, and beautifully in tune with nature's physics. So the next time you feel the wind brushing past your skin, remember, it's not just air moving. It's the breath of a planet, driven by sunlight, spun by rotation, sculpted by mountains, and reshaped by human hands. But there's one mystery we haven't yet explored. When warm rising air cools and condenses, wind gives birth to another spectacular phenomenon: clouds. Why do they form? Why do they take such different shapes? And what can those shapes tell us about the invisible motion of the air around them? Every cloud begins as a story of transformation, a dance between invisible vapor and the relentless laws of thermodynamics. Imagine a parcel of air rising through the sky. As it climbs, the surrounding pressure drops, the air expands, and in doing so, it spends energy, losing internal heat without exchanging a single calorie with its surroundings. This is adiabatic cooling, and it's the heartbeat of cloud formation. When that rising air cools enough to reach its dew point, the magic temperature where water vapor can condense, the invisible becomes visible. Tiny droplets or ice crystals emerge, clustering around microscopic particles floating in the air. These tiny particles are known as cloud condensation nuclei, dust, salt, soot, or pollen that give water vapor something to cling to. Without them, the sky could cool endlessly without ever forming a single droplet. Meteorologists love precision, so they've given names to these invisible heights in the sky. The lifting condensation level, or LCL, marks the altitude where rising air first becomes saturated, usually where puffy cumulus clouds start forming on a summer afternoon. But if the surface heats strongly enough, the air can rise on its own, no mountain or front needed. That's when we reach the convective condensation level, or CCL, the height where buoyant air spontaneously condenses. This is the birthplace of those cotton ball clouds that drift lazily across blue skies. And here's where the magic accelerates. When vapor condenses into liquid, it releases latent heat, energy stored within the phase change itself. That heat boosts the buoyancy of the air parcel, sending it climbing even higher. The result? A feedback loop of rising, cooling, condensing, and rising again. It's nature's own engine powering towering cumulonimbus clouds that can reach the edge of space. Now, if you've ever lain on your back watching clouds morph and stretch, you've probably noticed that not all clouds are created equal. Some form delicate strands high in the sky, cirrus, Latin for curl of hair. Others are thick and gray, spread like a wool blanket, stratus, meaning layer. And then there are the dramatic cauliflower-shaped cumulus clouds, heaps of vapor driven by rising thermals. This poetic classification goes all the way back to 1802, when an Englishman named Luke Howard gave clouds their Latin names. Today, the World Meteorological Organization organizes them into 10 main genera, grouped by altitude: cirrus and its cousins up high, altostratus and altocumulus in the middle, and stratus and stratocumulus down low. But the shape of a cloud isn't just decoration, it's a diagnosis. It tells us about the stability of the air. Stable air resists vertical motion, spreading clouds into wide, flat layers. That's why stratus and nimbostratus bring long, gentle rain. Unstable air does the opposite. It rises easily, building vertical towers. That's how we get cumulus and cumulonimbus clouds, the kind that light up with lightning and thunder. When you see a giant anvil-shaped cloud spreading across the horizon, you're actually looking at a vertical race between heat and gravity, the cloud rising until it hits the stable lid of the stratosphere. The atmosphere itself is drawing a line, saying, you can go no higher. But there's more than heat at play. The winds themselves carve the sky into motion. In a convective storm, rising updrafts build clouds skyward, while downdrafts, cold air sinking from the top, drag rain and hail back down. These two forces compete, defining the storm's life cycle. Sometimes the downdrafts crash so hard that they hit the ground and spread outward like invisible shockwaves. These are microbursts, one of aviation's most dangerous phenomena. And then there's wind shear, the change in wind speed or direction with height. It might sound subtle, but it's the difference between a harmless summer storm and a supercell thunderstorm capable of producing tornadoes. When wind shear tilts a cloud's internal circulation, it helps separate updrafts from downdrafts, essentially allowing the storm to feed itself for hours. Even mountains get in on the action. When strong winds rush over ridges, they set the air oscillating in waves, lee waves, like ripples on an invisible sea. At the crests of these waves, the air cools, condenses, and forms smooth, lens-shaped clouds known as lenticular clouds. They hover motionless even as the wind races through them, so perfectly shaped that they've often been mistaken for UFOs. Below them, turbulent rotors spin in violent circles, their motion sometimes revealed as rolling volutus clouds. Pilots know to respect these, because where the air looks like it's rolling, the turbulence is often fierce enough to shake an aircraft apart. Here's the fascinating part. Clouds don't just react to the atmosphere, they reveal it. To a trained observer, clouds are like fingerprints of the invisible. Layered stratus, stable air, gentle lifting. Towering cumulonimbus, instability and strong convection. Billow-like waves, wind shear slicing through different layers. Even on a global scale, clouds trace out the great movements of air. Ahead of a warm front, clouds stack in a predictable order, first thin cirrus, then thicker cirrostratus, then altostratus, and finally nimbostratus, bringing steady rain. In contrast, a cold front, where air rises rapidly, erupts with cumulonimbus clouds and sudden downpours. High above all of this, at the edge of the troposphere, the jet stream leaves its own cloud signature. Cirrus clouds often trace its path like silk threads in the sky, while sharp breaks or discontinuities mark the zone of strongest winds. Meteorologists and pilots still rely on these clues, reading the sky like a map to navigate the world below. When you next look up at a sunset streaked with cirrus clouds or a storm boiling with cumulonimbus clouds, remember, you're not just looking at vapor, you're seeing energy in motion. Every curl, layer, and shadow is a snapshot of temperature, pressure, and wind, all wrestling for equilibrium. Clouds are the atmosphere's handwriting, its way of telling us how it feels. And yet, for all we understand, there are mysteries left unsolved. Cloud condensation nuclei, those tiny specks that birth droplets, still hold secrets that ripple through global climate models. Understanding their role could help us predict how Earth's clouds and rainfall might change in the decades ahead. Next time on Foe's Curiosity, we're staying in the sky but trading thunderclouds for something smaller, lighter, and far more surprising. We'll ask, how can seeds fly without engines or muscles? What aerodynamic tricks do they use to stay aloft? And what can engineers learn from their designs? If you enjoyed today's journey through the clouds, make sure to subscribe to Foe's Curiosity on YouTube and follow us on Instagram for behind-the-scenes science and visuals from our upcoming episodes. Until next time, stay curious.